Just have a few more things to say to finish up from last time. The last thing that I want to explain is how to make a density matrix. And I sort of discussed this last time in response to questions, but now let's do it. Okay, so the one that we'll talk about in particular is the thermal state. So the density matrix of a thermal state is rho equals e to the minus beta h. H is the Hamiltonian. Now, the density matrix is an operator. Okay, so when it has two legs and its matrix elements are calculated like this, and since it has two legs, that means that it should be a path integral with two cuts. That is, two openings where things are unspecified, one for each leg. And the thermal density matrix is actually the simplest path integral, and it's one that we sort of already talked about. It's just the path integral on a strip of size beta. Because this, well, we already discussed the matrix elements of this operator. And we said that the matrix elements with an e to the minus beta h in here are given by just putting phi 1 and phi 2 on the two cuts. So the only difference now is that I'm writing this as an operator. Before we were writing the matrix elements. So this is on space. I've drawn this as if this is a 1 plus 1 dimensional, but this is general. It's a path integral on space times an interval of length beta. From here, we can now calculate the thermal partition function. Z of beta is the trace of rho. Remember the density matrices, well, when you do a path integral, the state or density matrix in this case that you make is not normalized. Okay, so the trace of normalized density matrix would just be 1, but I really mean trace of this rho is e to the minus beta h. So that's the sum in the field basis. That's the sum over phi 1 of phi 1 e to the minus beta h phi 1, which is the sum over phi 1 of the path integral with a phi 1 at bottom, phi 1 at top, and size beta. Okay, so remember what these pictures mean. They're all integrals, and this integral is just a path integral where we put boundary condition phi 1 at the bottom, and we put boundary condition phi 1 at the top, but then we sum over phi 1. So we're really just allowing phi 1 to be anything, but putting periodic boundary conditions on this path integral. Okay, so this is just periodic boundary conditions. We can rewrite this as just a path integral on the cylinder of size beta. What does this picture mean? This picture just means we do the usual. We do the Euclidean path integral d phi e to the minus SE of phi, where now the phi fields live on this cylinder and therefore are periodic under shifting by beta in that direction. Okay. So the upshot here is that the trace, so this is our formula that we wanted, and this is an important result. The upshot is that the trace glues the cuts together. So even if we don't care about quantum field theory on funny manifolds like cylinders, even if all we care about is quantum field theory in real time, in Lorentzian signature, in the real world, we can use topology in Euclidean signature in this case as basically a trick for doing calculations at finite temperature. Questions? So one thing we were discussing last time is when are Euclidean path integrals useful? My answer was they're useful when you're interested in states that are prepared by nice Euclidean path integrals. And what we've just seen is that the thermal state is one of those. So that's a good thing. So let me add operators into this. Talk about the correlation function at finite temperature. So let's define G at temperature beta as a function of x1 and x2 to be 1 over z of beta trace O of x1, O of x2, e to the minus beta h, where O is some operator. We could also write that, and sometimes I'll write it this way, as O of tau1 x1 vector, O of tau2 x2 vector, with a beta subscript to indicate the temperature. Now we could write this density matrix as a path integral and reinterpret it in terms of operators and so on, and go through exactly what we did for calculating the trace. But it's clear what's going to happen. We're just going to end up with the same path integral, but now with these operators inserted into the path integral. Okay, so this is, let me write it this way, 1 over z of beta times the path integral on the cylinder, now with operators inserted, O of x1, O of x2. But the important thing is that, so tau, here, the Euclidean time direction, is the direction around the torus. And that means, well, these are now operators that are living on a, sorry, I said torus, cylinder. These are operators living on this cylinder. And so it's periodic if we move these operators around, because they live on the cylinder. So what does that mean in terms of the correlation function? Well, tau is the direction, tau is the time direction that's being identified. So the conclusion is that this is periodic under tau goes to tau plus the inverse temperature beta. I'll write it this way. G beta of t vector x. I've gotten rid of one of the arguments because if we're in flat space, then everything's translation invariant. This depends only on the difference. So G beta of t vector x is equal to G beta of t plus I beta vector x. The I is there because this is the Lorentzian, this is the regular Minkowski time. Okay, so thermal correlation functions are periodic in imaginary time. That's what that says. This is called the KMS condition. Good, so I gave a path integral argument for the KMS condition by saying that the path integral that calculates this correlator is just on a cylinder, so we have some obvious periodicity. Of course, anything you can do with the path integral, you can, at least in principle, also do in operator language. So in this case, you can derive the KMS condition directly from the trace formula by manipulating this trace and using the cyclic property of the trace. So I'll give you, I'm not going to work through the details, but I'll give you a hint. If you bring out the time dependence of these operators by writing O of tau x is e to the h tau, O of x e to the minus h tau, then you can manipulate this trace and use the cyclic property of the trace to bring some operators around to the other side, and you can derive this formula. So I'll leave that as an exercise. Derive KMS from trace. Okay. Any questions? Yeah.
So the operators need not commute with h, right? In the first line?
Yeah, these operators don't commute with h.
So I'm just wondering what determines the positioning of the e to the beta h in that equation?
What determines it here?
Yeah, which is in the middle.
It's just a definition. We could, I mean, by the cyclic property, we could put it either before or after. If we put it in between, then that's the same as flipping the two operators. In this case, well, if there's some parity symmetry and these are the same operators, it doesn't matter. But if we had two different operators, it would matter.
So this is your shot, this is the definition.
Yeah, I just picked a convention to, yeah.
Oh,
Yeah, this is the definition.
Whenever you want to compute the expectation value of an operator, it's like the trace of that operator times rho.
Yeah, that's right. Okay. So the next topic that I want to discuss
I guess another question could be, how do you specify that ordering of path integral?
Yeah, good. That's part of the topic that I want to discuss now. But the answer is that in Euclidean signature, you don't. In Euclidean signature, everything commutes, and you don't specify operator orderings. There's only one. So only when you go to Lorentzian signature that you have to specify operator orderings, and that's what we're now going to talk about.
So how do you know whether you compute this thing or what you
Ah, sorry. Okay, it's a little, yeah, good. It's a little different at finite temperature. Let's see. At finite temperature, the operators, the only correlator we talk about is the one where the operators are ordered by imaginary time. Okay, so in other words, the correlator that we talk about at finite, and I think the other ones just don't make any sense. If we tried to do the trace, it wouldn't converge. So the correlator that makes sense at finite temperature is the one where they're ordered in imaginary time, and that's the one that you would get by slicing up this path integral by inserting a complete set of states. Yeah. Good. Okay, so what I want to do now is to discuss some basic properties of Euclidean and Lorentzian correlators and explain how they're related to each other. So, let me start with a few properties of correlators in Euclidean RD. I'm assuming that these are local operators, correlators of local operators at separated points. x1 not equal to x2, not equal to x3, etc. Okay. In other words, there can be interesting and important delta functions that don't obey the properties I'm going to describe. Okay, so first of all, they're independent of ordering. So in Euclidean signature, there are no commutators. 5x1, 5x2 is equal to 0. The second thing, which I'll call 1 prime, is that the correlators are single valued. I'm calling this 1 prime because this is really the same as, this is really just another way of saying number 1. So what does single valued mean? That means that there are no branch cuts. Okay, so if we have point 1, x1, and we have a point x2, and we have some correlation function that involves these and possibly some other points off somewhere else. That if we follow this correlation function as we move point 2 around point 1 and back to where it started, then it must be single valued. It cannot go through any branch cuts as we go through that procedure.
This is at 0 temperature now.
Yes, this is all on the plane, RD now. Some of this carries over to other situations, but a lot of it gets more complicated. So, for example, in a conformal field theory, the 2-point function is O of x1, O of x2 is equal to x1 minus x2 mod minus 2 delta. And I'm going to write this suggestively as x1 minus x2 squared to the minus delta. And the point is that as long as we're in Euclidean signature, so there's a non-integer power here in general. And so there's potentially a branch cut. But as long as we're in Euclidean signature, where both of these points are in RD, the distance between the 2 points, the squared distance between the 2 points is therefore positive, and therefore there is no branch cut. So if we take this positive quantity and put it up in the exponent with a log, we're never going to get the log of a negative number. It's always going to be a log of this positive number. Okay, so this has no cuts.
Could you explain why positive distance implies no branch cuts?
Yeah, so this is e to the minus delta log x1 minus x2 squared. And log has a branch cut, so we have to be careful with that and worry about it. But then this argument here in the log is the positive distance squared, so that's staying away from the branch cut of log, so we don't have a problem. I mean, as a totally practical matter, like if I take this function and I plot it along this curve, it will be a nice plot, and it will come back to where it started. Okay. Anything else? Okay. Maybe I should say a word about CFT. So we're gonna talk more about CFT, but for now I just threw those words out there, and some of you have probably not seen CFT. So a conformal field theory is a special kind of quantum field theory, and we're going to talk about what conformal field theory means and what it's good for. But the provisional definition that I'm using just for this discussion, or the fact I'm using, is that in a conformal field theory, you can choose a basis of local operators in which the operators have definite mass dimension. So that when you rescale the argument of the operator, the effect on the correlation function can be determined by dimensional analysis. So that's the provisional fact that's the only fact I'm using here. So in this case, the operator O is an operator of mass dimension delta, and dimensional analysis gives us this dimensional analysis together with like translation invariance gives us this form for the 2-point function. That's where that came from.
Is this single valuedness in the Euclidean signature really, like, should we take it as an axiom, or we can prove it?
Yes. Sorry. We have two choices, and this applies to all the properties that I'm discussing. Okay, so there's two ways to think about a quantum field theory. One is that you can think about the axioms, you can think about it as being defined in Euclidean signature. And you can write some axioms for what you'd like the quantum field theory to be in Euclidean signature. And then you can try to make sense of the physics of the Lorentzian theory. In that case, with that point of view, these are axioms that I'm writing. But an alternative is to start with some axioms in Lorentzian signature, like causality and other nice things that we'd like quantum field theories to obey. And then you can analytically continue from Lorentzian signature to Euclidean signature. And the rough statement, or caveats, the rough statement is that these two things completely agree with each other. So that the axioms that I'm writing in Euclidean are equivalent to the axioms that you would write if you were starting in Lorentzian. There are caveats to that statement. There are assumptions that go into the proof, and people still worry about these things, but we're just going to leave it at that, I think. Number two, Euclidean correlators are reflection positive. So what does reflection positive mean? It means that if I draw the Euclidean configuration, say I have a 4-point function of 4 identical operators at these 4 points. Well, you'll notice that this is reflection symmetric about the middle line. So this is a reflection symmetric configuration. I should probably give these operators names just to be clear. Like if this is O1, then this had better also be O1. If this is O2, this had better also be O2. And I'm assuming that these operators are Hermitian operators. This is reflection symmetric, and therefore the correlation function must be non-negative. A very useful thing to keep in mind is that, well, first, one way you can think about this is that it's symmetric under reflecting in Euclidean time. Okay, because these are Euclidean correlation functions. It's right. If it's symmetric under reflecting in Euclidean time, then it's positive. Okay, so these are Euclidean, so this direction here you can think of as the Euclidean time direction. But a useful thing to keep in mind is that when we do Euclidean quantum field theory, nobody tells us which way is the time direction. All directions are created equal. And so if I give you a configuration like this one, well, that doesn't look particularly symmetric if I think about time as going up, but I can draw a reflection plane that looks like this, and think of my Euclidean time as running perpendicular to it, and this configuration is symmetric with respect to that plane, so this one must also be positive.
I have a question.
Yeah.
So suppose I was given a model, say something like an Ising model, and I wanted to show that that particular model is reflection positive by computing this correlators. So I have to compute, like, by choosing every possible time axis and showing that this reflection symmetric configuration will be positive.
It's usually, no, that's usually not necessary. That's not how we do it. Let's see. Well,
I guess for lattice models it might be simpler, right? But maybe for continuum models.
If we have a quantum theory that's defined by a Hamiltonian, by a real Hamiltonian, then this is guaranteed. This is not something that we have to check. For reasons that I'll explain in a second. Likewise, if we have a quantum field theory and we can show that it has good factors, that it has a complete set of states with positive norm, and has good factorization properties of correlators into that complete set of states, then again, we're done. We've proved it for reasons we'll see in a second. There are situations where there are quantum field theories that are not reflection positive, but they come from, for example, Hamiltonians with I's in them. And they can arise, those can be interesting, they can arise in StatMech, but they can't arise in good unitary quantum systems.
I have a question.
Yeah.
Why does reflection positivity imply correlator is greater than equal to 0? It's not.
That's the statement. That is the statement of reflection positivity. Yeah.
I think you're doing Euclidean quantum mechanics, the commutator of x.
Sorry, that got muffled. Say it again.
Oh, let's say you're doing Euclidean quantum mechanics, and you could consider the commutator of x and p. The fact that that would be divided the first thing you got, like p not a local operator, or is that what's going on?
Yeah. So the analogous statement in Q of t is that phi of x times its conjugate has a delta function. So that agrees with, yeah.
Does this apply when an operator is on the boundary?
What do you mean by on the boundary? Do you mean on the dash,
Yeah.
on the center line?
Yeah.
No, it does not. Okay, so we could ask if, yeah, that's a good question. You know, that also looks, if we had a 5-point function with that thing, that kind of looks symmetric. It does not apply to that case. And we'll see why from the proof that I'm about to give.
No, this is a statement that norms are positive, right? But if you insert an operator in the middle, then where is its corresponding operator?
Well, that's why it's done.
Oh,
That's
okay.
why it doesn't work. Yeah. Yeah. Okay, so the quick way to understand this, and I put it proof in quotes because it's a good way to understand it, but it's incomplete. If you want to know why it's incomplete, I can come back to that. But it's just to write down the path interval. Okay, so let's think about a reflection symmetric configuration. This is a path integral, so this one. This is a path integral with an insertion of phi of tau 1, x vector 1, phi of minus tau 1, x vector 1, and then other things, but they all come in pairs, and then e to the minus SE. But SE itself is integral of a local density. So I can take this exponential and write it as e to the minus integral of the Euclidean Lagrangian density over tau greater than 0 times e to the minus integral LE of tau less than 0. So this is actually well, I can write it this way. I'm going to insert a complete set of states on the dashed line. So then this is an integral d phi naught of vector x of something squared. So that something squared is the path integral d phi of tau 1 vector x1 e to the minus SE integrated over the half space with boundary condition phi naught at the top. That's square. So what I've done here is I've just packaged one of the phi's, a phi in the upper half plane with a Lagrange density in the upper half plane, phi in the lower half plane with the density in the lower half plane. So we get the representation that looks like this.
Phi naught is like on the boundary.
Sorry?
Phi naught is on the boundary.
Yeah, phi naught is the value at the middle, the reflection plane. And this is just a sum of positive things, so this is also non-negative. And you can see where this would go wrong if the action, like if the Hamiltonian were not Hermitian, or the action had some funny, some, say, imaginary coupling constants in it or something like that, then this argument wouldn't go through. This wouldn't be the integral of positive quantity. I assumed here that the Euclidean action is real and parity even. The reason I assumed it's parity even is that there's some orientation flips. When I wrote this as something squared, that involved a flip of orientation. Now, if that flip in orientation were to come with a minus sign, like if the action were parity odd, then we'd have a problem. If you do have an action if you do have terms in the action that are, so I'm not going to go through the details, but if you look at this more carefully, if you have terms in the action that are parity odd, then in the Euclidean action, they must come with an I. So then these two things will cancel out, and you'll get a unitary theory. Interpretation of reflection positivity is that this is the Euclidean avatar of positive norms. This is the statement that the theory has positive norm states. So to make that precise, let me define O of tau x dagger to be O dagger of minus tau x. That should have been x vector. That's a definition. We're going to see why that's a good definition in a second. If O is a real operator, then we can drop this dagger on the second one. So then dagger only acts on the time, Euclidean time. So with this definition, if I write the correlation function O minus tau vector x, O of tau x, then as an operator equation, this is the expectation value in the vacuum of O of tau x vector dagger, O of tau x vector. And that is the norm squared of the state O of tau x vector on vacuum. Yeah.
Isn't it a little weird to call this a definition? Because as long as the Hamiltonian is Hermitian, then if we just think of that O of tau is defined as like the Heisenberg operator, then if you take its adjoint, it's just going to negate time. It's just going to flip. It's going to switch the ordering of the e to the plus h tau and minus h tau on either side. Just take tau to minus tau.
Yeah. The point is that Minkowski space positions are invariant under dagger. So, but that's a choice. Or I mean, I'm not saying there are other consistent choices. So I'm taking it as a definition, but it's really the only reasonable thing you can do.
But it also follows from the Heisenberg definition of what O of tau means, as long as O is Hermitian and or yeah. As long as H is Hermitian.
Yeah, that sounds right. That sounds right. Yeah. Yeah.
Yeah, as long as H is Hermitian, then this follows from the definition.
Yeah. Yeah, why did I mean, the reason I called it a definition is because when I write something like this, I'm talking about Euclidean fields, and yes, they have operator interpretations. It's the operator. So there's an operator called O, which is using the operator formalism, for which what you're saying is correct. That the operators have, the dagger on an operator means the adjoint, and you can use the usual definition of adjoint to figure out what that is. When I talk about these Euclidean correlators, well, I kind of think of these as different as a different object, and this is a definition for the Euclidean field. Now they translate into each other, so you have to make them agree. But I guess that's why I was thinking about it that way. We could think about it either way. You could think of them as
To
operators.
think of them as Heisenberg operators, that's like you're starting from a Lorentzian theory and then analytically continuing to Euclidean signature, right? But what if I just start with a theory with Euclidean signature, just
Well,
give
yeah,
a bunch of operators?
I agree. That's why I called it a definition.
exactly.
Yeah. It kind of is a matter of where we start. If we're starting with Euclidean fields, then I'd like to call it a definition. Okay. Okay, good. So that's reflection positivity. I didn't write the full statement of reflection positivity for you. I just wrote some examples. The statement is that anything that's reflection-y like that is positive. But actually, the full statement of reflection positivity is more than that, because it also allows for superpositions. Norms, not only of a single operator acting on vacuum, are positive, but if we put any linear combination of operators here, it would be positive. And the full statement of reflection positivity is what you would get by putting an arbitrary linear combination here, squaring it, and then rewriting it as a correlation function. That's the full statement. I'll leave it up to you to actually write it down. I'm not going to write the formula.
So reflection positivity did assume that the operators were also.
No, it's not required. I may have, let's see, I assumed it when I wrote this, but if I just put some daggers here, then that's the statement for non-Hermitian, for general operators.
So you're not using hermeticity?
No, I have not used hermeticity of the operators in this argument. I mean, a general operator is just O1 plus I O2. So you can always split it into its real and imaginary parts and apply what I've said here. So some of what I've said so far carries over to other manifolds. For example, if we consider Euclidean theories on the D-sphere, then pretty much everything, maybe even everything that I said carries over. I'd have to think about it. I think probably everything carries over because they're highly symmetric. But you can imagine that things change if you start talking about the theory on say, a non-symmetric Euclidean manifold. Then you don't really have statements like this. The last, property 3. Is the statement, well, let me write a formula. So if I integrate over points in Euclidean space of some weighting function f, and then insert some local operators O1 of x1, O2 of x2 to On of xn, act on vacuum. The states that you can make this way the set of states that you can make this way is dense in the Hilbert space of the quantum field theory. Roughly, this means that you can make any state by inserting operators in Euclidean signature and also allowing for superpositions. It's not quite true technically, it's only dense, but that's sort of a good way to think about it, the first order. And the point I want to make here is just that you can learn pretty much everything there is to know about a Lorentzian quantum field theory by studying Euclidean correlation functions in principle. All the information is there. This goes by the name of Reconstruction theorems, and is something that people proved back in the 60s, 70s or so. Is there a question?
Yeah, I mean, if I think about this as like a regular Lorentzian quantum field theory, and I imagine that the O's could be creation operators, then I would think it would be obvious that I could construct any state with a definite number of particles that way, and then I could get any other state. I mean, that's a complete basis for the Hilbert space, isn't it? So is there more to say than that?
That's all there is to say about the free theory.
Okay.
Everything I'm saying is for interacting units. Other questions? Okay, now I want to go to Lorentzian. By Lorentzian, at this point, I'm talking about flat space, although a lot of things will carry over. As I emphasized last time, a Euclidean quantum field theory and a Lorentzian quantum field theory are not two different theories. They're the same theory. This is especially powerful in this relativistic setting because observables in Euclidean and in Lorentzian are often related by analytic continuation. So I want to explain that analytic continuation carefully. I'm going to start with an example, which is our CFT two-point function that we had a few minutes ago. Let me write it again. It was O of tau 1 x1, O of tau 2 x2 was the distance squared. I'm just separating out space and time now. So tau 1 minus tau 2 squared plus x1 vector minus x2 vector squared to the minus delta. Now, what we'd like, so that's the Euclidean. If we're in Euclidean signature, we said that this is completely well-defined. There are no branch cuts or anything that we have to worry about here. It's a completely well-defined expression in Euclidean signature. We'd like to go to Lorentzian. So roughly speaking, we need to continue tau to IT. Then the correlator becomes minus T1 minus T2 squared plus x1 vector minus x2 vector squared to the minus delta. Now we're taking a non-integer root of something that can go negative, and when it goes negative, we do have a branch cut that we have to worry about. So this is unambiguous space-like separation but for time-like separation, it becomes, well, for time-like separation, the thing in there is negative, so let me extract a minus sign here and write it as t12 squared minus x12 vector squared to the minus delta times minus 1 to the delta. This t12 notation, this is just shorthand that I'll start using for the difference between t1 and t2. Okay, so I've just made it so that this thing is now well defined, no branch cuts, and I put the branch cut into this term here. Was there a question? Yeah.
I guess it's just a CFT question. Maybe. So the delta, what values or what
Um,
is that?
Any positive number at this point.
Okay.
Positive real number, yes. Okay, so this thing here is e to the plus minus I pi delta. And so we have an ambiguity, which is whether we should choose the positive or negative sign here. This corresponds to which way we go around the branch cut. I like to think about this as an analytic function of tau 1. Okay, so what I mean by that is that we're going to take this original Euclidean correlation function, freeze everything except for tau 1, and then look at the complex tau 1 plane. On the complex tau 1 plane, if tau 1 is, so we're going to freeze everything else. So this line is the Euclidean line. If we're along here, tau 1 is real. And this line here is the Lorentzian one. Okay, and what we just described, that branch cut we just described, is a branch cut that looks like this. There's a corresponding one on the bottom. The branch point starts at t1 is equal to t2 plus mod x12. And this one starts at t1 is t2 minus mod x12. And what I've just shown is that, so if the points are time-like separated, then that means we're somewhere along this cut, right? Because in Lorentzian signature, we're somewhere along here. Tau is pure imaginary. And if they're time-like separated, we're above the branch point. So the points of physical interest at time-like separation are points that are on this cut. And we can, of course, reach them two ways. Well, when you analytically continue a function, you have to start from some open domain. So imagine we knew the function in that little open domain. And then you can analytically continue. Okay, so if we follow that function along this curve, we'll end up with one value. And if we follow it this way, we'll end up with a different one. So one of these will give the e to the I pi delta, and the other one will give the e to the minus I pi delta. And the physics point is that these are the two orderings of the Lorentzian correlation function. So one of them is O of x1, O of x2, and the other is O of x2, O of x1. Yeah.
Why did you label both the crosses as T1 equals T2 plus minus? What was that?
These x's, these are the branch points of this function. In other words, that's where this function is 0. So that's where we have to choose a cut if we go past that point. What?
That's nice.
What's nice?
Oh, just that you expected it to have two values depending on the two orderings when they're time-like separated, because that's when they can be causally related, and that's exactly what we see. And we expect them to commute when their spaces.
Yes,
separated.
exactly. So this is how locality in Lorentzian real-time physics is encoded in correlation functions. It's the fact that in Euclidean signature, everything commutes, so there's just one correlation function. So along here, no branch cuts. How does that give us commutators and the kinds of things we expect in Lorentzian signature? Well, they show up as branch cuts in the correlation function. And this is one way of explaining why operators don't commute in Lorentzian signature. It's because as you go to time-like separation, you hit branch cuts. You need to pick a way of going around the cut, and the way that we do that is by assigning these the two operator orderings. Now it's more than that. Like operator ordering is not just a notational convention. Operator ordering, they're really operators acting in a certain order. Okay, it's how you multiply the matrix elements. So there's more to it. But the point is that if we let's think of it in reverse. Let's think about it in reverse. So say we started in Lorentzian signature, and we just had two totally different objects. The O of x1, O of x2 was one object that we had in our Lorentzian theory. And O of x2, O of x1 was another thing we had in a Lorentzian theory. Now, these have to commute at space-like separation. Okay? So we know that there's some region on the complex plane where these two functions agree with each other. Well, if there's somewhere that they agree, they can only be, and then elsewhere on the complex plane, they can only be analytic continuations of each other around some cut. So this was guaranteed to work out this way.
So this imposes a restriction on the form of the correlators in Euclidean.
Sorry?
This imposes a restriction on the form of the Euclidean correlators?
Only that they're single valued. You mean the fact that this branch cut can't start too soon?
Yeah.
Yeah, that's right. That's right. That's a very non-trivial constraint on the Euclidean correlation functions. It's pretty trivial on two-point functions, but it's very non-trivial on higher point functions. In formulas, the point is just that O1, O2 is x12 to the minus 2 delta minus 2 delta e to the plus I pi delta. And I'm writing this time-like separation. And O2, O1 is x12 to the minus 2 delta times e to the minus I pi delta.
You have to get similar forms even without the formula there. So like, have the branch cut where you want it, right? You would also just have to depend on x1, 2.
Yeah, for two-point functions, the two-point functions in a massive theory they have the same analytic structure as this, but they can be more complicated functions. Same branch point. Okay, all this business about contours and going around branch cuts and all that, I find the best way, to me it's the easiest way to think about it. It's not a great way for calculating things. You don't want to have to like, if you want to calculate something, you don't want to have to like draw these pictures and like follow contours and figure out which one was the plus I delta and which one was the minus I delta, etc. So actually, what you usually see, and the best way for calculations, is what's called the I-epsilon prescription. This is a shorthand for dealing with these branch cuts that we've talked about. And this is just that we shift line I-epsilon. So the first one has a T1 minus I-epsilon minus T2 squared plus x12 squared to the minus delta. And the other one has a plus I-epsilon, but is otherwise the same. In these expressions, you have to take the principal branch for the, there's a log coming from this exponent. You just have to take the principal branch for log, and then these expressions will agree with the ones that we had determined by going around the cuts. Okay, I just told you which one was the plus I delta and which one was the minus I delta. So let me tell you where that comes from, because that is not an arbitrary choice. One of these really, you really have to, it's important which one is which when you go around the cut. Okay, so why is that? Well, let's look at the imaginary part of the Lorentzian correlator, O of T1, O of T2. I've set x1 equal x2 equal 0, just because the positions won't really matter here. And let's take T1 greater than T2. And the reason I took the imaginary part is because we're just trying to decide if it's a e to the plus I delta or sorry, e to the plus I pi delta or e to the minus I pi delta. So we should look at the imaginary part of the correlator to determine which sign is the correct one. Okay, so if we want all of these manipulations we're doing to agree with the operator formalism, so let me write it out in operators. This is e to the I h T1 O of 0. E to the minus IH, T1 minus T2, O of 0, e to the minus IH, T2 on vacuum. The Hamiltonian doesn't do anything when it hits the vacuum, so I can erase those terms. And now what I'm going to do is insert in here a complete set of momentum states. Then this becomes the imaginary part of integral d4p. The Hamiltonian acting on a state of definite momentum will just give p0. So this is minus I p0 t1 minus t2. Then there's an overlap of O of 0 with P. There's a P with O of 0. And finally, there's the measure for this sum over states. So what does that measure look like? Well, it's an arbitrary function of p squared, which you could think of as the density of states in this sum. It has to be rotationally, clearly has to be rotationally invariant. The density of states can't depend on the vector components. And secondly, it can only be supported at positive energy. So there's a theta function of p0. This density of states here is greater than or equal to 0. Is there a question?
How did you get rho and the theta function from the previous line?
Sorry?
From the previous line, how does the measure with rho?
Well, I didn't really do anything. I just gave it a name. There's got to be some measure. It has to be positive because we're just summing over all the states. And it has to be rotationally invariant. Like, it can't be rho of p0 vector p. That would not be allowed. It's got to be rotationally invariant. So I had to make a function of p, which was positive, and a function only of the invariant. So I just gave it a name, rho of p squared. So that's where this came from. Where did this term come from? Well, that's just because there can only be states in the spectrum with positive energy or non-negative energy. Yeah.
Why are we doing this? I know it'll end up giving us the answer we want, but
That's why.
I mean, it just seems like black magic, if that makes sense. Like you're just doing it to do it. Like,
Well,
I would have never thought just like, okay, I'm just going to start inserting momentum states. Like, is there any like motivation for like why we would just pull this trick out of our hat?
why the imaginary part?
No, you just inserted momentum states, and I'm just asking like.
No,
what was motivation for that decision?
just because it works, but it also
Okay.
also I'm doing it because it will teach an important lesson.
Like, how would you have thought to do this? Like, the first person who did this, what the hell was he thinking?
Why insert momentum states there?
Because he can.
Well, let me write the conclusion and then ask me again why the hell I'm doing this. Okay. So the conclusion is that the imaginary part of the 2-point function in momentum space is non-negative, and in fact is equal to this rho of p squared theta of p0. Okay, I've just written a Fourier transform here. Well, sorry. No, it also has these guys. Let me erase them. Okay, so if we just interpret the integrand here as the momentum space 2-point function. Sorry, I forgot to mention. This part here is something squared, something mod squared. Okay, so this part is positive, this part is positive, this part is positive. So everything in here is positive. Okay, so the momentum space 2-point function is positive. And now going back to why do this, I don't. What?
The e to the minus I p0.
Well, that's not part of the Fourier transform. The Fourier transform is the integrand.
Okay.
Right. Okay, so first of all, let me just say that it's generally true and always a useful thing to know that the imaginary part of the two-point function is positive and related to the spectrum. This is used everywhere. This is like all over high energy, it's all over condensed matter. So it is like a very well-known thing. I know that's not a great excuse for why I did it.
It's like the optical theorem.
It's kind of like an optical, well, it's similar to the optical, yeah, it's,
I guess there you have
It's-
two scattering or something.
yeah, it enters, it's kind of the optical theorem kind of uses this on an internal line. I mean, another way of saying it is that if you're used to perturbative Q of t, then if you have the exchange of a mass m, if you have the exchange of something of mass m, and I'm going to mangle the conventions here, so forgive me for that, I'll just pick a convention. Okay, if you have a exchange of a particle of mass m, then it looks like this in a Feynman diagram. And there's two important things here. One is that the mass is positive, and the other is that the coefficient is positive, the residue, okay? And what this so the imaginary part of something real like this is the coefficient, because there's a pole. The imaginary part of the pole has a delta function, p squared minus m squared. Okay, so when you have the exchange of a particle of mass m, that gives an imaginary part, which is a delta function at the mass of that particle. So we're in a theory with exactly stable massive particles, it's true that the imaginary part of the Green's function is the spectrum. It's the spectrum of particles being exchanged, in this case just the delta function. So the way to think about the more general situation is that it's a smeared version of that. Okay? So if you have an exactly stable massive particle being exchanged, you get a delta function at the mass of the particle. More generally, you smear it out, it's some function, but unitarity still requires it to come with a correct sign. I probably messed up all sorts of I's and stuff in that discussion, but that's the idea.
And why are you assuming stable particles?
No, here I was talking about stable particles because I was describing the exchange of a stable massive particle. If the particle is unstable, then
It implies that whatever we interpret as decay width or something, that has to be positive, right?
yeah. So if you put in a width here, then then the imaginary part will now be some kind of Breit-Wigner peak, and the unitarity will fix this to have the right sign. I think I got the wrong sign maybe, but it has some sign. Okay, for our purposes, I'm not going to finish doing the Fourier transform and actually tell you which was the e to the I pi delta and which was the minus I pi delta. But this is how it's determined. Okay. So this fixes the choice when we were going around branch cuts. This tells you which one is O12 and which one is O21. To complete the calculation, you have to actually do the Fourier transform and see which one is the positive one, and check this positivity condition. So good. So note that unitarity did two things for us in this story. So first of all, unitarity fixed the coefficient of the Euclidean correlator. So the Euclidean correlator was x1 minus x2 to the minus 2 delta. And unitarity fixed this number here to be positive, because that's reflection positivity. And we've already explained how that's related to positive norms. That's a Euclidean statement. And now we've seen unitarity enter again to tell us which way around the branch cut is 012 and which way around the branch cut is 021. Okay, so it's entered sort of in two logically distinct ways. Okay. Let's stop there for today.